I just made myself a bunch just in case. All right, so when we look at liquids, we're going to look at the qualitative description of liquids. And just so you know, there's about 3 or 4 questions on the exam that are related to the gas law one. So what you just saw, there's 3 or 4 questions like that where there'll be a sentence and you got to decide what's happening, what's going up, what's going down. And there is practice online, so you should be able to do those just to get an idea of what they look like, okay? So first thing when we talk qualitative description, again, we're looking at the list of things that we saw before. The first thing is all liquids are made up of tiny particles. The particles may be atoms, molecules, and sometimes, rarely, ions. Okay, so this is rare. And so it says rarely. The reason I'm saying rarely, it does happen. Sometimes you can melt salt. Has anybody ever tried to melt salt on their burner? It's really hard to do. We're talking 5,000, 6,000, 10,000 degrees Celsius just to get it to melt. That doesn't happen at home, okay? But it can happen in real life, so we put it in sometimes ions. For the most part, liquids are going to be molecules or atoms, okay? Very rarely atoms even, because we're going to see that for atoms, the only one that's a liquid commonly is your bromine. That's at room temperature, right? We talked about francium and cesium. They're on the border. They get warmer. They can become a liquid. So even for atoms, it's not that common, but it's very common for molecules to be liquids. Most common one you know is water, right? It's a molecule commonly found as a liquid, okay? These particles are held together closely by weak attractive forces. And this is compared to our gases. So our gases had this long distance and they had no attraction, right? You can't see it again? Sorry. So the gases were far apart. Still not showing up? It'll take a second. Come on. Okay, maybe no. Gotta love technology. There we go. Okay, so that's a gas. It's far apart. They have no attraction at all for each other. When we look at a liquid, we're going to put them in a container, and these two are going to be in contact with each other. So they are in contact. They are definitely closer together. That's why their density is higher, right? So these ones are in contact. So this is a liquid. They're in contact with each other. Very different from a gas. Gases are very far apart. So if you guys were in contact with each other, right now you would be gases because you're not touching each other, right? But if I said all of you need to sit in the front row, now you'd be right next to each other and you'd be more or less in contact. You'd be bumping shoulders, right? That's more like a liquid. You're really compressed together. If you're already in the front row and you're already touching shoulders, is it easy for me to squish you together closer? Can I make you get even closer? Kind of. So one of the things that I use for my example, gases don't touch each other at all. Liquids are touching each other, but maybe like holding hands. So they're close to each other, but they're not super close together. When we go to solids, they're going to be even closer together. They're going to be hugging. So if everybody in this room were in a giant group hug, which really doesn't work well with COVID, right? But if you were in a giant group hug, it would be much harder for you guys to move around, right? What we see with liquids is they have contact. So there's some kind of contact. So I'm going to use you guys as my example. I've only got 3 of you, so I'm going to do 3 in my row. So if you guys can put your hands out for a second. Okay, so I'm in contact with her right now, so we would be a liquid. Now I'm coming over here, and I'm in contact with her, but I'm no longer in contact with her. Still a liquid because I'm still in contact. Now these two would still be in contact with each other. I'm not going to make it over each other heads. But now I can move over here and be in contact with here. So as I'm moving, I'm able to move, but I'm staying in contact all the time. I'm not escaping from them. You recall that? As long as I'm touching them, I'm still a liquid. But now, I let go and I run away. When I let go, I become a gas because I'm not in contact with anything. Does that make sense so far? When we talk about when something boils, what does it do? It breaks contact. Okay? So no more contact anymore. I'm separated from them. It's now a gas. But while they're in contact, it's a liquid. Can they move when they're liquid? Could I move? Yes, I could move, right? I was able to go from one to the next to the next. That's because they have a weak attraction for each other. When we get to solids, they're going to have a really strong attraction. They're going to be the hug, right? So if everybody in this room was hugging, would it be easy to move around? Not at all, because we're going to be one giant mass of people, right? Just a big clump. It's really hard to move when you're a solid. All right, so they have weak attractive forces, and that's one of the big things that we have. So weak attractive, and they're held closely together. We're going to talk about strong attractive forces when we get to solids. The liquid particles move rapidly with an average kinetic energy that is dependent upon their absolute temperature. This is exactly the same as we saw with gases. The particles move faster when they get hotter, okay? So higher temperature means more kinetic energy, and that means they move faster. Now, I'm going to give you an example of what happens here. So I'm going to be holding their hands again, and I'm going to try to move faster. So I was real slow. I was able to go, tell the hands here, holding here and then holding here, right? And then I went here and then I went to here. But now I have to do it faster, so and so if I'm going much faster, I'm going to escape easier. Does that make sense? Because it's going to be hard for me to keep in contact with everybody because I've got all this energy I'm just going to escape. So that's when something boils, is when it gets more energy. So how do you make your water boil? What do you do to it? You add heat, right? You add heat energy. What does that do? It makes those particles move faster. The temperature rises up. Then, as the temperature rises, then eventually it gets to the point that it's moving so fast it can no longer hold on, and it escapes into a gas. Does that make sense? So that's the basic process that we're seeing when something boils. We're going to go into boiling later, but that's the basics of it. It's just moving so fast it can't hold on anymore. All right, next one. Because of their motion, the particles of the liquid are free to slide past each other, but because they're attracted to each other, most of them do not escape. So most of the time, the liquid stays as a liquid, but a few escape. Notice that we do say most, only a few escape. These ones turn into a gas. So all liquids always have something called vapor pressure above them. There's some kind of vapor that's on top because it's always turning into a gas all the time. So you'll look like, if you've ever had a sealed glass of water, something like a bottle of water, you'll notice that on the edges there'll be a little bit of water from the vapors that went up. Did you guys all see that? So those vapors are because there's always a vapor above every liquid. Every liquid has a vapor above it. So we always have that. The big thing here is that they can move. Okay, so particles are free to slip past each other, so they move. That means that they can flow, they can do all kinds of things, but they don't leave each other very often, don't break apart. Basic characteristics of gases. So, we talked about this before. When we talk about definite volume and no definite shape, those are the two things that we're going to look at. So they don't have a definite shape. I'm going to start with that one. So if I take, you'll think I'm an alcoholic here. I've got my martini glass, my tall boy, I wonder what kind of alcohol that's for, and my beer stein, put a little handle on it. So I've got all these different containers, right? And I'm going to pour some liquid into it. So if I pour the liquid into here, it's going to take the shape of the container. If I pour that liquid into here, it's going to take the shape of the container. And take the shape of the container, right? So all of them take the shape of the container. I have to do one more to honor my children. You get those sippy cups that have those weird things that you can never clean, right? It's going to take the shape of that sippy cup. Okay, so whatever the shape of the cup is. But did you notice I didn't fill the cup? None of them are filled. That's because they do have a defined, I missed the word no here, I apologize. This should say no definite shape. They have a specific volume, a specific volume. So the volume here is 1 cup, 1 cup, 1 cup, 1 cup, and 1 cup. It takes the shape of whatever container I pour it into. I pour it out of one, I pour it into the next one. It's going to have the same volume no matter what I do. So when you're in lab and you're measuring something in a beaker, let's say I want to measure 10 milliliters and it's in one of those beakers. Let's make it a small beaker like this, right? And I measure 10 milliliters, it's going to be flat like this. But if I want to put it in a tall graduated cylinder, that's the tall skinny guy, if you remember, I put it in there, now I've got more graduations and I can see, oh, that's 10 milliliters, not somewhere between 6 and 12 or 15, right? I can really see it more accurately because it's the same volume no matter whether I put it in the tall, skinny glass or I put it in the short, fat glass, doesn't matter, okay? Same total volume no matter what. That means definite volume, but it does not have the shape. It takes on whatever container you put, it's gonna fill that container to the maximum volume that it has, okay? But it doesn't fill the container, and that's different from gases. We know that liquids are more dense than gases because they're in contact with each other. Okay, because the liquids have to be in contact. Am I going over the time? I don't know what time it is, I apologize. The clocks in here are horrible. I got 5 more minutes, okay. All right, liquids are not compressible, and this is important for when you're looking at your braking system. So on your brakes in your car, and this is, so I can't push them together closer because they're already in contact, right? So they're not really easily compressible. So if I have this braking system, this is very, very much expanded, but here's my brake pedal. And let's make it a little bit fatter so it hits the hose, and then this is filled with fluid, which is a liquid, right? And then over here, you've got your tire. This is not exactly correct, but you've got your big tire here that's going to stop. So what it does is it just pushes on that to stop it, right? If you've ever seen like isn't that showing again? Well, my art wasn't that good anyway, but I'll try to get it just so you can see it. I apologize. I don't know why it does that. So basically what happens is if this is my brake pedal and this is my wheel, I go like this and I push on my brake pedal, it's going to push on the wheel and that stops the wheel from spinning. Just something that stops it from spinning, right? If you've ever had a salad spinner, you just push down on a button and it stops spinning when you push that button. So this is what's happening. You're pushing here, and then in between, there's this brake fluid. So we have this brake fluid. That brake fluid is not compressible. So I push here, and the whole thing shifts, and it stops the wheel. Does that make sense? And just kind of push, and then you release it, and now it can spin again because there's nothing pushing against it. So what happens if I have an air bubble? So if you've ever changed, it's going to go away again, isn't it? If you have an air bubble, sorry. It'll come back up in a second. There we go. If you have an air bubble in there, what'll happen is is that air bubble is compressible, right? So if you've ever changed the brake line, has anybody done the brakes on their car? I used to work on a car. I had a 65 Mustang. I used to work on it all the time. It was so easy to work on. I now have a modern car, and those are horrible to work on because I can't do anything. But anyway, I changed the brake line in my car when I was in college. And you have to make sure that you have no air bubbles in there. And those can be the size of a pinhead, tiny, tiny air bubble. Because they're compressible, when you push on your brake, it goes like this, and it doesn't move. So here's my wheel, and I'm pushing, and nothing's happening. That's because the gas is compressing. Instead of moving the whole liquid with it, it compresses, okay? And so it's a little tiny air bubble. And that's one way that you can tell that you've got a little air bubble in your car, is if you get your brakes get soft, it's usually because they've got a little air pocket in there. That means the brake fluid got a little bit low, and it allowed a little bit of air in there, and as soon as that air goes in, it compresses. And your brakes get soft, and you can't stop as well as you used to. That's usually just because your brake fluid's low. It's a really simple fix. Usually they have to drain it and clear it and do all kinds of good stuff, but it is a lot of work to get all of the bubbles out. You have to make sure all bubbles are out. Anyway, liquids are not compressible. That's the main thing that we're seeing there. Gases are very compressible, liquids are not. Next, liquids do flow. So you can see a river flows, right? So most people can remember that they do flow. And if they hit a rock, what's going to happen? They're going to splash, right? So that's diffusing. So liquids flow and they diffuse. So they keep going the same direction until they hit something, and then they start spreading out. And it can be hitting each other. It doesn't always have to be some other thing like a rock. Liquids expand slightly when heated, very small differences. We're not going to worry about them, so we're going to say it's very slight. So you don't need to worry about those. What does a lot? Gases expand a lot when they're heated. Liquids, not so much. Okay? And we'll do, I guess, next time, and then we'll do the very last thing next time. And then our exam should be the following Tuesday. You guys said 1 week from then, right? So not this Tuesday. Hopefully you have Monday, Wednesday classes and enjoy your holiday weekend. And then we will see you the following Tuesday. Sorry. What we're really looking for in this case is what can make more of the gas? So how can I make more gas? Okay? And that is going to, by increasing the temperature, more particles can escape and turn into gas. Okay, because there's a higher vapor pressure, because I've increased the number of particles that are turning into a gas. Does that make sense? So by increasing the temperature, more of it turns into a gas. If there's more gas present, that means our pressure is going to go up. Our vapor pressure is increasing. Okay? Why do the particles escape more if it's hotter? You guys have probably seen this at home, right? So if you take a glass of water and you put it in your fridge, and a same size glass of water and you put it in your window so it's nice and warm, which one's going to evaporate first? The hot one will, right? Why does that happen? So what does temperature have to do with energy? What kind of energy are we looking at? Is it kinetic energy or potential energy? We'll start there. Kinetic energy. What does kinetic energy tell you? What is it? It's the energy of motion. It's not storage, it's motion, right? So this is saying I'm starting off with a bunch of particles that are moving slowly. I heat them up, they're going to go faster and faster, right? So let's say my hands are trying to hold hands, right? I'm trying to hold hands. I'm going faster and faster and faster. You can see they're going to start to slip off of each other because they're moving so fast. Does that make sense? The faster it moves, the easier it breaks apart because they're trying to hold on. So think about a whole bunch of kids and, you know, the whip the snake kind of game. Have you guys all played that? Where they're all holding hands. The faster they move, the more likely that tail is going to whip off. Why? Because they're moving really fast. It's hard to hold on to each other. Same thing happens here. As they warm up, those particles move faster. As they move faster, they're going to escape from the liquid. They're going to turn into a gas. And that's how the gas pressure increases, the vapor pressure increases, okay? A couple of other things that I mentioned that it happens at the surface, and that's going to now we're going to talk about how that impacts what we see happening. Oops, no, let's go off. Sorry, somehow I didn't pick that guy up. So what does that mean as far as evaporation? So I've got this container like this, and a different one like this, and stopped screening, sorry. Come on. There we go. So I've got these two containers, and they have the same amount of liquid in them. So we're going to say they have the same amount of liquid. That's supposed to be in the container, not outside, but I don't get an A for coloring today. Which one is going to have more particles easier to escape if it only occurs at the surface? Okay, let me ask you. You're mopping your floor, right? And there's some water on the floor and you want to, how can you make it dry faster? What do you do to make it dry faster? You spread it out, right? So if there's a spill on the floor and you let it just sit there as a puddle, it's going to take a long time to evaporate. But if you spread it out, make a bigger surface area, then it's going to evaporate faster. Does that make sense? So we always spread it out with a mop. We kind of spread it out, and then that'll start to help dry off. So what we see is this one has lots, oops, try that again, has lots of vapor pressure because it's all happening at the surface. This one has a number of particles coming off, right? If we were to look at this, though, in the same, hold on just a second, let me cut an image here. In the same spacing, in that same space, we might have the same number of particles. So we could see in this one, I've got 1, 2, 3, 4, 5, 6, 7, and this one I should have 7 also. And then I'll take another pocket, not those guys. Can't grab the right one. And I move those, trying to get this guy, and I move it over here, and it should also be 7 and 7 and 7. So in that same size, it's the same total vapor pressure. Does that make sense? So while this has more vapors, the vapor pressure is the same. These two have the same vapor pressure. They're going to have the same number of lines coming off of the same area, but the one has a bigger surface area, so it looks like there's more gas coming off. Does that make sense? But the vapor pressure is the same because they're at the same temperature. As long as they're at the same temperature, the vapor pressure will be the same. And why does this occur most at the surface? And that's just a kind of a theory question. So why does it occur more at the surface than in the center? If you're a particle, and I just use this room as an example. So everybody's sitting in this room. If you're in the middle seats, let's say this room was full of people instead of half empty. But if they're in the middle seats and there was a fire, who would be the first one out of here? Who would be the first people out of here if there was a fire? There's people here on that corner, maybe this person here, this one, top corners, right? They'll be the first ones out because they're closest to doors, right? And then maybe the people at the outside edges because they're on the surface. Does that make sense? So the people at the surface will get out faster. The people in the middle have to wait till the person before them gets out, right? Same thing happens for these particles. So if I'm a particle, I'm going to make it black. If I'm a particle and I have to escape from here, I'm just going to grab another piece. So I'm going to zoom in. We're going to make a zoom in on this. So I'm looking at my my liquid particles, and I have this particle, this particle, this particle. So these are my actual particles, right? You would never see them like this because they're way too small. But this guy is bonded to this one, and 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 this one. For it to escape, it has to break all of those bonds. If you look at this guy here, it's bonded to just a couple. So it has fewer places that it has to escape. Even if it had more, let's say 3 more, it still has less than the other one does. Does that make sense? So for that one to escape, it can escape very easily. So let's say this guy escapes all of those bonds. What happens to it? It moves a little, It moves a little bit. It does not want to let me do it. It moves up to here, let's say. But now it's still surrounded by more particles, and they all bond to it. So it's constantly, it may escape a little bit, but then it gets caught again. And so it can't really escape for very long. Sort of like when I was moving from person to person. I might have let go of her for a second, but then I was on the next person because there was another one right there to catch it. Does that make sense? So it has to only occur at the surface. It doesn't have enough energy to escape from anywhere but the surface. So that's why evaporation occurs at the surface. Any questions? Okay. Next, we're going to look at what is vapor pressure. So we already talked about it. And the vapor pressure is the tendency of a liquid to vaporize. So the vapor pressure is how much and how easily a liquid turns into a gas. Okay. One thing that we can do to affect the vapor pressure is change the temperature. Higher temperature equals more vapor pressure, higher vapor pressure. Okay, so that's one of the easy ways. One of the other ways that we can do it is to change the chemical. So every chemical has its own vapor pressure, whatever that happens to be. So this is one that you probably can, again, think about something you're doing at home. So I'm going to have this container and its partner, exactly the same shape and size, right? So these two are exactly the same. One is going to be filled with water, and one is going to be filled with, let's say, acetone. You ever spilled acetone on your countertop? Which one evaporates faster? The acetone evaporates faster. Does everybody follow that? Okay. So this guy evaporates faster. Oops. So what does that mean about its vapor pressure? That means that it escapes more because it's turning into a gas easier. That means there's more gas present. That means it has a higher vapor pressure. I'm going to abbreviate VP for vapor pressure. Okay, so why do we see a difference there? This has to do with how well bonded they are. So I'm going to use my hands as an example. So if I hold these two hands together and they have to break a bond, that breaks pretty easily. If I take all of my fingers and I hold them all together, it's harder for me to break. Does that make sense? So it's really easy to break one, it just kind of slips past each other. This is a weaker bond, that means it turns into a gas easier, it doesn't take as much energy. For me to break it when I have all my fingers holding on together, I've got to move really, really fast and then it'll eventually break. So we're looking at the strength of the bonds, and this tells us that it has weaker bonds I don't know if you can see that. I know it likes to slide down. Come on, grab. Weaker bonds are going to give a higher vapor pressure. Sorry. Okay, so higher vapor pressures come from higher temperatures and weaker bonds, weaker interparticle forces. Okay. Any questions so far? So why do we care about the vapor pressure? And that's going to come up in the next